So good afternoon, everyone. Find myself in a special spot, the last talk of the last day of the workshop, of the last workshop for Sensam. So there have been some conspiracy. Someone, I guess, Janelle and maybe Alex, maybe Chin are involved in putting me in that location. But I'm happy to talk to you about the stuff that we did in the last 10 years. And I would like to emphasize first a couple of topics that are not covered in my talk. And those are related to the areas of coupled ocean atmosphere studies that I did with Paolo Rizzoli. Paolo is here. One of the highlights of my participation in Sensam is the opportunity to work with Paolo and to collaborate in development of these models. And then the work in urban ecology, which actually I think is quite significant, and also I'm not going to be able to talk about it today. I'm going to be talking about some of the regional climate studies, and in there we looked actually at two things: impact of land use change, irrigation on regional climates, and the impact of climate change on regional climates. And that's the part I'm going to focus on, the impact of climate change. But there have been significant work done also on impacts of irrigation on climate. Output of my activities in the last 10 years, about 22 research articles. Some of them already published, some of them are in the pipeline, including some significant ones in Nature Geoscience and Science Advances. The Science Advances one just got actually accepted last week, and I'm going to talk about some of those results today. There have been 2 MIT doctoral theses. Those of you who have been, remember Rebecca Gianotti was a student here who did her PhD, and Mekki Sid Ahmed is finishing actually in very soon. 5 research associates with their names here. 2 of them moved to become assistant professors, and we're happy to have Professor Im with us today. And Peng Fei Shou, who worked with me, and Paula is also a professor in Michigan Technological University. So what I would like to focus on today is really regional climate change impacts in Asia. And this is really summarizing in several studies that we have done. So I will just be covering the highlights of those studies. This is work done by Suchul Kang, Yunsin Im, and Jeremy Paul, all collaborating within this group. Most of the focus that I had in my group in the last 10 years is really about regional climate models. And regional climate models, as I think mentioned yesterday by Andrew in his presentation, are quite suited to study climate and climate processes in settings like the maritime continent, where we have complex geography and islands of really very small scale that are not usually resolved with climate models. GCMs do not resolve them, so you cannot really talk about impacts in those kind of settings. So the general way that we use regional climate models is you basically have a domain nested within a GCM. So the GCM provides the lateral boundary condition, and that allows you to focus all the computer power within the inner domain and to go to very high resolutions. Some of the simulations I'm going to show today for the maritime continent, they go down to about 10 kilometers. And so that resolves things like Singapore and its geography and so on. So there's going to be quite a bit of animation. If you like those, the credit goes to Shuchul, who have made all these slides. But this is like shows you the degree of details that like we have in a place like around Singapore. We started with a model called REXCM3 a few years ago, and each of these is like a PhD. Marcella, Gianotti, Winter, those are all some of my PhD students, and each of them contributes to developments of components of the model. So eventually we decided to call it the MIT Regional Climate Model. And that's the tool that we use in most of our studies over Asia, over Africa, and other regions, North America too. It's a 3-dimensional sigma coordinate hydrostatic compressible primitive equation RCM. So that's the jargon we use to describe these tools. It has representation for all things like aerosols and chemistry, rainfall, land surface processes, all kinds of things. And those are the references for the updates for that. a few years ago, we started looking at the issue of climate. We brought in this new concept of looking into, everyone is looking at temperature. A lot of the studies that we looked at, we heard about today and yesterday, is about what's going to happen to the global temperature. We propose that maybe a more appropriate way or more efficient way, if we would like to talk about impacts and impacts on health and comfort, like we heard yesterday, and that we focus on a different variable which we call wet bulb temperature. And if you go to any meteorological station, you'll find basically two thermometers. One of them is called the dry bulb thermometer, and the other is called the wet bulb thermometer. And so these are really standard measurements that are done every day, everywhere. The dry bulb thermometer gives you the temperature, the regular temperature that everyone is familiar with. The wet bulb thermometer is usually used to be able to retrieve information about humidity. So if you tell me what the temperature and what the wet bulb temperature, then I could tell you what the humidity is. So that's how it's being used usually. What we are proposing is that this variable in itself is a valuable variable that's measurable, that's observable, that there is a huge records of it in the past, and that we should use it in itself. So what the definition of the wet bulb temperature is that the temperature that an air parcel would attain if cooled by evaporating water into it until it saturates. So that's how it's defined. And so it's a measure of both, if air temperature and humidity. And so if we think about heat waves and heat stress, people don't care only about temperature, they care about temperature and humidity. That's what makes things uncomfortable. So if we think of the cooling of the human body, the main process that's really responsible of cooling of the human body is perspiration. So heat gets basically, metabolism generates heat at the rate of about 90 watts per meter square, and the human body, a healthy human body, has to get rid of that heat. And the most efficient way to do that is perspiration. Okay? And the way that happens is that the inner core of the human body is at 37 degrees centigrade. All of us who had children and your children get fever, you take them to the hospital. When the temperature is above that, you know you are in the danger level. You get at a point where you just like take a towel and cool them down if the temperature gets to that. We all experience that. So that's the inner core of the human body, and you don't want it to go above that. The skin of the human body assumes 35 degrees centigrade. Actually, again, the skin of the human body assumes the wet bulb temperature. So you could think of the human body as a big bulb. If the thermometer had a small bulb, this is a big bulb, and the temperature of the skin assumes the wet bulb temperature. And so if the temperature in the inner core is 37, and if the temperature at the surface is like 33, 30, 20, then you could get rid of the heat by just the circulation of blood and then conduction of the heat outwards. When the temperature of the skin, however, approaches the 37, then you cannot get rid of heat. And here you get into really not just comfort, you get into survival issues. So the heat stress that I'm going to talk about today is really a different type of heat waves that we are talking about. It's not the regular heat wave that makes you uncomfortable. These are heat waves that could kill you if you remain out there in like for 6 hours or so. Until recently, until a paper we published recently, that used to be like just a theoretical concept. It was never simulated that the temperature, the condition would reach that level. And what the paper we published actually in Nature Climate Change a year ago or so, it showed for the first time that this is a possibility. With climate change, it's possible that you could experience conditions like that. And so then you start limiting survivability, habitability of regions as a result of climate change. And that's why this paper got a lot of attention. We projected for the region around the Persian Gulf that this region here would be the first region on Earth to reach that level of heat conditions. And that only in summer because of combination of high humidity and high temperature. These pictures do not show very well, but this purple color over there points to locations where that threshold of about 35 degrees centigrade is reached. Okay. So you see it here in histograms in places like Dubai, which is a popular spot for tourism. You know, you could easily reach that threshold. It's not something that's happened every year, but as a possibility that it could happen like once every 30 years. when it happens, if humans exposed to that, and here already we are averaging temperature over 6 degrees over 6 hours. If you are exposed to that, then that's very, that basically could kill you, even for a healthy person. You don't have to be old or thick or anything. It's just you cannot survive that condition. So that has been simulated for places like Dubai, Abu Dhabi, and Qatar. So that's the work we did over the Persian Gulf. And building on that, we started looking at maps like this. I hope this map shows very well because it's very important for this presentation. So if you look at the maximum wet bulb temperature that had been observed anywhere on Earth, you could see that regions where the wet bulb temperature had been high are shown in yellow and red. And indeed, the area around the Persian Gulf is an area where you have very high values. So that when we picked on it and we did our first study on that, that's quite a logical choice because it's a very warm area. And especially that's during summer. Remember that there is very high seasonality around that region. The climate there is not like Singapore where it's warm and humid all year round. It's really just in summer, and it gets very, very severe around the Red Sea and the Persian Gulf. But what's interesting in this map, when you blow it up, that's not the only place where such conditions happen. There are actually other regions where that really is an issue, where the wet bulb temperature could be high, and that's in South Asia and in Eastern China. And the difference, and what makes this really significant, and this is the topic for the paper we just got accepted in Science Advances, is South Asia, is that these regions where we are finding high wet bulb temperature conditions correspond to regions where you have very high populations. So it's no longer like the Persian Gulf where you have small populations, mostly wealthy, oil-rich countries that can afford to have air conditioning. Here you have huge populations concentrated in areas where agriculture is the main activity, and people have to spend significant amount of time outside in the fields. And so we decided to look more carefully into these regions. So the first results I would like to share with you are with South Asia. This is a study that Yoon Soon Im really did a major part of it in collaboration with myself and Jeremy Paul, and this is the subject for the paper that just got accepted. You notice here the maritime continent, which we all associate with really being warm and humid region. It doesn't show up as much. When you come about this extreme condition, these are extreme heat waves, this is not the hottest spot for it. So the other region that's of concern is this eastern region of China, where also the wet bulb temperature reaches very high values. The approach we follow, in summary, is very careful selection of the GCMs we use as boundary conditions. We are picking here CCSM, which is the NCAR model, the German model, the MPI, Max Planck Institute, and the Access model, which is the Australian model. And we run these models for controlled climates, for climate with mitigation, and climate without mitigation, RCP 8.5, which is the business as usual. We do dynamical downscaling using our model, MRCM. In addition to that, we do bias correction with observations, and then the results of that is what leads to our impact assessment. This is the methodology that we pioneered in this paper, and we usually look at two scenarios: emissions that's mitigated, RCP 4.5. You could think about it more like what the Paris Agreement talked about, and RCP 8.5, which is actually business as usual, which is the most likely thing that's going to happen, with the kind of political environments we have. And if you look at the past, usually the worst case scenario is what gets realized. So it's not really unusual. When you keep business as usual, when people did that like 20 years ago, if you look back now at what were different scenarios, what had been followed actually is exactly what was the worst case scenario 20 years ago. So if you want to project 20 years from now, the best guess is that the worst case scenario will be what's happening. And I think what we are seeing in the political situation and how people are seriously taking climate change points to that being quite a reasonable guess. So here now, let's focus first on South Asia. This is the geography of it. You have the Tibetan Plateau, but you have this valley here, which is the Indus flows in this way over Pakistan, and the Ganges flows this way in India and Bangladesh. This is a very low-lying area, which actually proved to be quite suitable for high wet bulb temperature conditions. Another feature is you have significant irrigation, one of the largest irrigated areas around this region. And irrigation, believe it or not, actually, it cools the temperature, but actually in terms of wet bulb temperature, it warms it up. That's actually something for those of us who are thinking about cooling Singapore, you have to think about. Reducing vegetation, enhancing vegetation could actually make the temperature cooler, but it could actually make the wet bulb temperature higher because of the humidity impact is more significant than the temperature impact. But here you see this is what the observations, this is what MRCM is saying, and this is the difference, So we very carefully check the models against the observations. We do that also using stations data, and I was told that I have only a few minutes, so I'm going to move a little bit quickly. But we have histograms here. We come up with histograms similar to the Southwest Asia, in which we project over these locations in India and South Asia in general what kind of future temperature conditions will be. And here, this is all projected in terms of what you could call of it as a thermal comfort indicator, which is based on the National Weather Service description of caution, extreme caution, danger, and extreme danger. And you see here for the South Asia, the conditions are already, you get significant heat waves, and so you are likely to get deadly heat waves as you move into the future. And so that's the case for the South Asia. Here you look at it at the National Weather Service heat index, and you see the same thing, basically very, very extreme conditions that could happen in that region. The problem with that is that that region is a region where the population density is very high, is among the highest population density in the world. The GDP is among the lowest, and people work in agriculture. So that combination of high population density, low GDP, necessity to work outside, when you have hazards from temperature conditions, then you're really putting a very, very lethal combination. So another region that we looked at is China, and for the sake of time, I'm going to skip that, but we get similar results for China. Let me just move to the maritime continent, which is the region of interest here. We looked at this region, and here, over the maritime continent, we looked at the stations. The data record we have is not as good as other regions, so we looked at only some stations, Brunei, Singapore, Medan, and so on, that we had data for. We made projections also into the future, but you notice that the values of the wet bulb temperature that you get here under these maritime conditions are not as severe as the values that you could see in South Asia or Southwest Asia. So here, using the same measures over the wet bulb temperature, and this is the National Weather Service classification, the colors are not very clear here. There is another line, so you don't get into the extreme danger. You only get into danger with this region compared to South Asia, where you get into extremely dangerous conditions. Again, even under business as usual, you don't get into the extremely dangerous conditions. So the last thing I would like to mention is really important for this region. We also looked at precipitation over the maritime continent. And the model we have actually does a very good job in simulating the distribution of precipitation. This is time, and this is latitude. And you see this is TRMM, which is the satellite data on precipitation, and this is what the model simulates. And here you have the changes that happened in that rainfall distribution. And what you notice is that there is a significant drying that happens around the period August, September, October, simulated by the model for this region. And what that really tells us is that, if you look at stations like you look at the Malay Peninsula or northern Sumatra, you see significant reduction in rainfall that happens during the time of January, February, March. If you look at the southern region, like southern Sumatra and Java, you see significant reduction in rainfall that happens during the July, August, September, October time scale. Singapore, falling in the middle, we simulate reductions that happens in both periods. So it gets effects from both sides, because on one side, it gets impacted by rainfall from both sides. What that really means is that seasonality of rainfall, and this is the important result, is that seasonality of rainfall is projected to increase significantly. So we developed the measure for seasonality by the maximum rainfall, the months of the maximum rainfall, the minimum rainfall, divided by the long-term average rainfall. And as a result, when you look at that measure, you see that seasonality of rainfall over places like Singapore is likely to increase by 33%. That's actually a very significant conclusion in my view. Actually, before we get into that, we understand why that's happening. The reason that's happening is because there is a strengthening of the monsoonal circulation that happens during this period. So you see that this is the climatology and this is the changes. So the changes are such that you have more subsidence in the southern part during this August, September, October period, and that results in significant reduction in rainfall. So these changes in seasonality have implications to several processes actually. You know, adequacy of reservoir storage capacity. Singapore has built all this storage capacity by building reservoirs to store water. And the one main design factor in designing those reservoirs is basically the difference between the maximum and the minimum flow, because you usually store water from the months of maximum flow to the months of minimal flow. So that's something that gets impacted by seasonality. Seasonality of dengue, which is something that we studied. This is the main topic of Mekki's thesis, which is done under SENSAM, is to understand seasonality of dengue, and that's likely to be impacted by changes in the seasonality of rainfall. Dynamics of peat. I think I read the paper, the PNNS paper that Alex and Charlie and their group, and one of the main impacts of climate change comes through the changes in seasonality. And so that could be a factor. Water stress for natural vegetation and forests is another factor. So for this region, we are projecting changes in wet bulb temperature that are milder than what could happen elsewhere in Asia. However, changes in seasonality of rainfall that are significant enough that could potentially have impact on processes that are important to society, things like reservoirs and water, disease like dengue and natural ecosystems. Okay, thank you.